Alrighty, hello and good afternoon. Welcome to Wednesday's lecture. Today we wrapped up our discussion of molecular orbital theory on Monday, and today we are diving in to a new topic, one that will be very important for those of you who are planning on carrying on, especially when you get to organic chemistry. And that is the topic of actually, I'm going to run out of room if I try to write it up there. Intermolecular forces. Intermolecular forces. And an abbreviation is IMF. All right, we're going to be talking about intermolecular forces today, probably on Monday as well. Now, let's so first off, good place to start might be what are intermolecular forces? Well, the definition for an intermolecular force, or intermolecular forces, are the attractive forces that pull molecules / atoms / ions, all of them, towards each other. All right. Inter means between, so between two molecules. Intermolecular forces, the attractive forces that pull molecules towards each other. And really, the key word here is attraction. These are the forces that determine, for example, what compounds are soluble in other compounds. If two molecules are attracted to each other, then one will dissolve the other, right? These are the forces that determine things like the boiling point or melting point of a substance, how much energy it takes to get that substance to change phases. All of those are related to these intermolecular forces, which, again, literally means force, the forces between two molecules. So the forces, the pull that different molecules have on each other. And really, again, the key word here is attraction. These are attractive forces. Now, we are going to look at, over the course of this lecture, possibly on Mondays as well. So I'm going to give you kind of the big picture. We're going to look at 3 different types of intermolecular forces. The first being, so the intermolecular forces that we're going to look at are London dispersion, forces. These are also known as van der Waals forces. You may know it by that name. London dispersion forces, dipole forces, and hydrogen bonding. All right. And if we were to rank these forces from the weakest to the strongest, the weakest would be London dispersion, the strongest would be hydrogen bonding, and dipole is in the middle, so it's weakest to strongest. listed as so. I want to let you know up front. We'll discuss why, and you'll see why as we talk about each one of these forces. But these are how they're ranked from weak to strong. And the reason why this is important, I'm going to give you the punchline, all right? The end of the movie, where this topic I'm going to do, I'm going to lecture this like I'm Christopher Nolan. I'm going to tell you the end first, and then as we move through the narrative of this intermolecular forces narrative, you'll then see how that plays out and why that's important. But I want to tell you the point up front so that you'll be able to keep it in mind as we move through our lecture today. So here's the set piece, the point of all of this. A species, all right, so that could be molecule, atom, ion, a species with stronger intermolecular forces will have higher, or I should say, will have a higher boiling point slash melting point slash freezing point than a species with weaker intermolecular forces. All right? And the reason why this is important is because what we're going to be building to, what you're going to see, not on exam 4, but on the final, you'll see problems testing on intermolecular forces that will ask you, for example, to rank a set of molecules from the highest boiling point to the lowest boiling point. And what that type of problem is testing you on is, can you identify which species, which molecule has the strongest intermolecular forces? That gets ranked highest. Weakest gets ranked lowest, and so on. So the whole point of learning these things is so that you can look at molecules and assess, okay, how high or how low are their boiling points? There's more applications than that, but that's just one example of why it's important. So I wanted to kind of put that in your head so you can be mindful of it, keep it in view as we move through each intermolecular force in sequence and learn about them, and then start applying that knowledge to the Lewis structures of molecules. All right. So let's dive in with our first intermolecular force. Let's talk about London dispersion. All right, otherwise known as LD is the abbreviation that I'll be using. So let's talk about London dispersion forces. All right, now, what are London dispersion forces? So I could start by giving you the definition, but instead I'm going to illustrate what it is, and then we'll end with the definition, just because I feel like it makes more sense taken in that order. So I want you to consider, we're going to do a thought experiment here. I want you to think about an atom of helium. All right, let's think about an atom of helium. Helium has 2 protons and 2 neutrons in its nucleus. All right, so we got 2 positive charges buzzing around there, or not buzzing around, they're just sitting there, right, with the neutrons. And then we have a 1s orbital with 2 electrons flying around. Now, these guys are moving all around this 1s orbital, right? They're constantly flying around, moving around. A blur of motion, a blur of activity. Now, I want to do a thought experiment. I want you to imagine, so the electrons are both trying to get as close to the nucleus as possible, all right? But they want to stay as far away from each other as possible. So when one electron kind of buzzes towards the nucleus, its momentum can carry it to the other side. And when it moves, it's going to, the repulsion of that blue electron that I showed moving over to this side is going to force that black electron to move away from it, right? Because they're both negatively charged and those charges repel each other. That will happen. But I want you to, for a split second, imagine that you're watching this on video and pause it. I want you to, in your mind, before the blue electron's moved over, but before the black electron has had an opportunity to be repulsed, let's pause that video and think about the atom as drawn. Okay? Think about this. For this split second in time, all right, and it's not very long, it's like a picosecond. But for this small moment in time, all of the negative charge is concentrated on the left side of the orbital, right? All the negative charges are over there, all the positive charge. So because both electrons are on the negative side of the orbital, there is a slight buildup of negative charge, what we call a partial negative. All right? I've never drawn this before, so I just want to take a moment to explain. This is a lowercase delta, which is the Greek letter for D. We've seen the uppercase, which is that triangle. This is the lowercase. And it looks like that. And it is used to indicate what we call a partial charge. So it indicates a partial charge, not a full-blown minus or a full-blown positive, but a partial charge. It's not that this has become an ion, but because both of the electrons are over on the left side of the orbital, that side of the orbital now has a partial negative charge, all right? Because that's where both electrons are. Because that's where both electrons are, and we have that partial negative, that means that the other side, where the electrons are not, has developed a partial positive charge. All right, for this split second moment in time. All right. So they're not permanent, it's not charged, it's not an ion, but for this moment, when both electrons are on one side of the orbital, we have this partial positive and partial negative. I want you to think now about the effect that this partial negative and partial positive will have on the next helium atom, on the helium atom this is closest to. Now again, the two electrons here are just buzzing around, hanging out like it's no big deal. The nucleus is stationary, right? It's not really moving, not dynamic, but the electrons do move. And the question that I have for you is, what effect do you think this this partial positive charge will have on the two electrons orbiting this atom? What effect do you think it'll have? Well, it's a partial positive. The electrons are negative, opposite charges attract. So what's going to happen is this partial positive will actually pull the two electrons to this side of the orbital. They will move towards that partial positive charge because they're negative and they're attracted to it. What does that create in this helium atom? Well, since both electrons are on the what's depicted as the left side of the orbital, it will create a partial negative charge on the left side, and it will create a partial positive on the right side. Now, if I asked you, right, that makes sense because the electrons are drawn towards that partial positive. Therefore, when they move towards it, they create the same imbalance in this helium atom as exists in the first. If you're wondering what happens to the helium atom another atom over, well, the answer is the exact same thing. Right? This atom, although let me reposition my nucleus a little bit. In this atom, its electrons are going to move towards the partial positive, creating a partial negative, and on the other side a partial positive. We can't see it, it's off frame, but that happens. And this kind of daisy chains, all right? This is London dispersion forces at work, all right? What London dispersion forces are, London dispersion forces are the attraction, the intermolecular attraction they're the intermolecular attraction created by temporary partial charges or I should say, hang on, I should say they are the intermolecular attraction created by partial charges created by the temporary we should say a temporary uneven distribution of electrons. All right, they're the intermolecular attraction. London dispersion forces are the intermolecular attraction created by partial charges created by temporary uneven distribution of electrons. And hopefully now you see why I started with the explanation of what it is before I gave you the definition of what it is. If I had told you it's intermolecular attraction created by partial charges, which are created by a temporary uneven distribution of electrons, you would have said what? But now that you've seen what a temporary uneven distribution of electrons looks like and the effect that that has on the atom next to it and the atom next to it, you can understand what this definition is telling you. Now, there's one thing I have to stress, all right? One thing I got to stress about this. And that is this. What makes London dispersion forces weak, all right? What makes this intermolecular force the weakest is this word right here. It is a temporary uneven distribution of electrons. Because it's So here's the thing. We built up this whole thing, right? And then one atom influences the next, and a kind of daisy chains, right? All of these attractions. Remember, this is a thought experiment, all right? This is a thought experiment where we said, okay, pause. Pause the video for 1 second. What happens when we unpause our video? What happens when we click, okay, play? Remember, this electron does not want to be close to the other. When we unpause this thing, what's it going to do? It's going to fly away, destroying this partial positive and partial negative, which is going to make this electron fly away, destroying its partial positive and partial negative, which will make this electron fly away, destroying that partial negative and partial positive, etc. So the second London dispersion forces are active, are created, they're destroyed because the electrons are constantly moving, all right? They're constantly in motion. So it's a very, very weak force because it doesn't last very long. It's a temporary partial charge. But there's a difference between temporary and non-existent. It's still there, even if it's just for seconds at a time. And it is an attractive force that will influence the boiling point, melting point, etc. Of any given molecule. So that is what London dispersion forces are. Let's talk about what atoms, molecules, ions experience London dispersion forces. All right. So London dispersion forces are experienced, or I should say exist, between any two species with electrons. All right. If your molecule has electrons, it will experience London dispersion forces. All right. So if you're doing a problem, for example, on an exam, and I give you a molecule and I ask you to determine the intermolecular forces that this molecule experiences, you should always select an answer that at least has London dispersion forces, right? Every molecule has electrons. So everything with electrons experiences London dispersion forces. So this should always be part of the answer. All right. It should always be part of the answer. Something you should keep in mind about London dispersion forces is there is a bit of a tiebreaker. All right, so something else you should know about London dispersion forces is the following. Remember that London dispersion forces are based on temporary partial charges. All right, and it is easier to form those temporary partial charges in larger orbitals. So the larger the orbital is, the more likely it is for the electrons to be imbalanced on one side of an orbital. And so the larger the orbitals are, and by larger I mean the higher energy they are, the stronger London dispersion forces will be. Kate, are there any species that don't have electrons? That is a great question. Technically, yes. Well, here. Picture's worth 1,000 words. I'll get back to this slide in 1 second. So Kate just asked a great question. Are there any species that don't have electrons? Technically, yes. H plus has no electrons, right? Because hydrogen has one electron and one proton. So if hydrogen has a positive charge, that means it has one proton and no electrons. This is the only species I can think of without electrons. And just for the record, I wouldn't throw this on a test. I'm not going to go that level of like trick question nastiness with you guys. But technically, H plus is hydrogen that's lost a electron, and hydrogen only starts with one, so H plus has no electron. So that's the only species I can think of that doesn't have an electron. I'm not going to throw H plus up there and ask what are the intermolecular forces operative in this species. That will not happen to you. So you don't need to stress about it. So for all intents and purposes, every molecule or ion or species that you will see on the test will have London dispersion forces. The reason why I phrase it that way is because technically you need electrons, and there is a species that doesn't have them. So I'm being correct in my words, but you do not need to worry about being tested on this exception or special case. Kate, you are so totally welcome. All right. Okay, so getting back to this business right here. So London dispersion forces exist between any two species with electrons, and the larger, or I should say, let's start with the, I should say, larger orbitals in other words, larger values of the principal quantum number result in stronger London dispersion forces. All right, and that is because in a larger orbital, the electrons have more room to move around, so they have more of an opportunity to create those partial negative and partial positive charges if they have more room to breathe. So with that in mind, I could ask you to rank the following molecules from highest to lowest boiling point. All right, rank the following molecules from highest to lowest boiling point. Now, whenever you see a question like this, what you want to read is rank them from strongest to weakest intermolecular forces. The highest boiling point will have the strongest intermolecular forces. The lowest boiling point will have the weakest intermolecular forces. And typically for these problems, you'll have to go through each molecule and figure out which intermolecular forces are present, which are active. Right now, we only know London dispersion, so these examples will only involve London dispersion forces, but for future examples, you'll also have to assess for dipole, and for hydrogen bonding as well. All right, but let's go ahead and rank these. Fluorine, bromine, chlorine, iodine. All right, let's take a look. Again, we only know intermolecular forces at this point, so that is the only one we're assessing. So we have to ask ourselves which one, or well, we have to. Sorry, hang on. We have to ask ourselves which of these have the largest orbitals, which have the smallest orbitals, because since they all only have London dispersion, the strongest London dispersion attractions are going to be in the orbitals that are the largest. The weakest will be in the ones that are the smallest. And you'll notice here that fluorine is right here. So N equals 2. Bromine is down here. N equals 3. Chlorine is right here. Its orbital energies are on, 3, sorry, so bromine is 4. My bad. And then iodine is N equals 5. Because iodine is on the 5th period, its orbitals are the largest. So if we're going to rank these from the strongest to weakest, we're going to put iodine in the strongest category because it has the largest orbitals. Fluorine is the weakest because it has the smallest orbitals. Again, we only have London dispersion going on here. Bromine is in second place for second strongest, and chlorine from this mix is second weakest. So that is how you would rank the boiling point from, okay, we just ranked from strongest to weakest, but what did we say? That is code for highest boiling point to lowest. All right, that is how you rank a group of molecules that only have London dispersion forces present. All right. Okay, so that is everything you need to know about London dispersion. London dispersion forces. Let's take a look at dipole-dipole, which I'll be abbreviating DD. All right, dipole-dipole forces. Dipole-dipole forces are, our understanding of dipole-dipole forces is related to our understanding of London dispersion forces. But the biggest difference, actually the difference between London dispersion and dipole-dipole here, I'm going to give you the definition first. But based on your understanding of London dispersion, you'll have some idea of what this means. Dipole-dipole forces are the attractive forces between two species the attractive forces between two species with partial charges that are created by a permanent by a permanent, uneven distribution of electrons. All right? The attractive forces between two species with partial charges, and these partial charges are created by a permanent, uneven distribution of electrons. What are we talking about here? How, or you know what we're talking about, actually. The question is how? How is this, how are these partial charges permanent? How is the uneven distribution of electrons permanent? This happens when you have electrons that are shared between two nuclei. So we're talking about a covalent bond where one element is more electronegative than the other. All right. You might recall when we first introduced the idea of covalent bonding, we have ionic bonding, right? Where you have in an ionic bond, electrons are taken by the more electronegative element away from the less electronegative element. Then in covalent bonding, they're shared between, right? And we said at the time, we introduced this idea that the type of bond was determined by the difference in electronegativity, all right? That the difference of electronegativity between the two atoms involved determined what type of bond we were dealing with. So, for example, we said a covalent bond forms between two atoms whose difference in electronegativity is less than 0.5. All right, if you took that difference and it was less than 0.5, that you had a covalent bond on your hands. Whoa, that's a little one-sided. There we go. We said an ionic bond is created when you have a bond forming between two atoms whose difference in electronegativity was greater than 2.0. Greater than 2.0. And this leaves this weird middle ground, right? What happens when your difference in electronegativity is between 0.5 and 2.0? The type of bond you form is called a polar covalent bond. It's still covalent. The electrons are still shared between those two atoms, between the two nuclei, but the critical difference is that they're shared, but they're shared unevenly, all right? When you are dealing with polar covalent bonds, the electrons are more attracted to the more electronegative element. All right. As a result, they spend more time around that nucleus, the electronegative nucleus. So this creates both a delta minus partial negative and a partial positive in the molecule. Or species, I should say. All right. Here's the way to think about it. When you have an electronegative, a more electronegative atom and a less electronegative atom. For example, let's take the molecule hydrofluoric acid as an example. We take as our first witness hydrofluoric acid, which fun story, Jesse Pinkman put this into a porcelain tub in season 1 of Breaking Bad, and that led to that amazing scene. If you know, you know. If you don't know, give Breaking Bad a watch. It's worth your time. So let's look. So the Lewis structure for hydrofluoric acid is, looks like this. H and an F. Now, hydrogen has an electronegativity of 2.1. And fluorine has an electronegativity of 4.0. So if you calculate the difference in electronegativity, it's 4.0 minus 2.1 comes out to be 1.9. This falls squarely in the polar covalent range. All right, so this is a polar covalent bond. We just say polar bond. What that means is the electrons that are in this HF bond are more attracted to the fluorine than they are to the hydrogen. All right? In fact, they spend more time around the fluorine than the hydrogen. And because they spend more time around fluorine, because it's pulling harder, it's more electronegative, a partial negative charge develops on fluorine, and a partial positive charge depends on hydrogen. The way to think about this is remember when you're kids, and this might date me. When I was a child, growing up, there was that one friend's house that had the Nintendo 64 right when it came out. And all the kids in the neighborhood would want to hang out at that house more than any other of the homes around. Right? Because that was the one with the console. That was the one that was more electronegative than all the homes around it. So as a result, that house had more kids in it on average than all the other homes. Did we spend all of our time there? No, because we all had to go back to our own homes, have dinner, and go to sleep in our own beds in our own rooms. But on average, we spent a little more time at that house than we did at all the other ones. All right? And that is what's going on here with the electrons. Fluorine, the more electronegative element, has the new console. All right? Whatever that is. It's I guess the PS5 now, right? Is the new one that everybody's oohing and on over. So the fluorine has the PS5. All the kids want to be at that kid's house because they have the cool new thing. So fluorine picks up a partial negative charge because the electrons spend a little bit more time on fluorine, than they do at hydrogen. And that's why these partial charges are permanent, because at no point does fluorine stop being more electronegative than hydrogen. It's more electronegative all the time. So it will always have that partial negative charge. All right? These partial charges are one way to depict the electronic imbalance in the molecule. Another way is you draw an arrow, and you put the arrowhead pointing towards the partial negative side, and then the tail of the arrow, you put a little hatch through it to make it look like a plus side, and that sits on the partial positive side, all right? And this thing right here, this is called the dipole moment, all right? This is, so on an exam that wasn't digital, right? Ours is digital. I can't put this type of problem on there, but like on an exam that you take in class, if class were in person, I would say, draw the dipole moment. And when you ask someone, when someone asks you to draw the dipole moment, they're talking about this arrow to show which portion of the molecule is negative, which portion of the molecule is positive. It communicates the same information as the delta plus and delta minus. It's just another way of doing that, and so you need to be familiar with the symbol. You need to know what it means, which is why I'm spending our precious lecture time talking about it. Okay, we're not quite done, but we need to open a new slide. So molecules that have dipole moments will arrange themselves in specific ways. All right, so here's, for example, a molecule of HF, and again, as we already know, we have a partial positive charge on the hydrogen and a partial negative charge on the fluorine. Now, when a second molecule of HF approaches this molecule from the top or the bottom, there are two ways it could do it, right? It could stack like so, come in where the hydrogen lines up with the hydrogen and the fluorine lines up with the fluorine, or it could stack where the fluorine lines up with the hydrogen and the hydrogen lines up with the fluorine. And it will never happen this way because the hydrogen isn't attracted to the hydrogen, the fluorine isn't attracted to the fluorine, because these are the same, right? These charges are the same. I don't know why I wrote two E's in same. All right, fluorine, HF, will never approach another fluorine in this direction. It will approach so that the delta plus on one hydrogen lines up with the delta minus on the fluorine, and the delta minus on the one fluorine lines up with the delta plus on the other hydrogen. All right. And the point is, our dipole moments control how molecules arrange themselves. All right, that attraction to opposite charges, repulsion by like charges, all control how these molecules configure themselves in 3 dimensions. And when one molecule moves, it affects all the other ones around them. There's like ripples of repulsion and attraction as it tumbles through space, right? Because there are other molecules that are up in this, right? There's other molecules of HF that are attracted or repulsed by different portions of the molecule, like this, bringing in another H to be close to this fluorine. And you can imagine more and more and more kind of building and arranging in this particular fashion. All right. Okay. Now, we're not quite done talking about dipole forces, if you can believe it. Let's talk about water. Now, it turns out that fluorine is a simple case because it's linear, right? There's only two atoms in it, and so determining whether or not it has a dipole is very, very easy. But it takes a little more work to determine whether or not there's a dipole moment for molecules that have more than two atoms in them. All right. As it turns out, it's not just enough to look at the difference in electronegativities, but you also have to consider the three-dimensional shape of the molecule, the Vesper geometry, in addition to the electronegativities, will determine whether or not your molecule has a dipole moment, whether or not your molecule is polar. Because as we'll see, it's possible, not in this example, but the one after, it's possible to have polar bonds and to have a nonpolar molecule. The geometry has something to say in that. All right, so let's look at that in a moment. First, let's look at H2O. All right. The Lewis structure for water. This is one way to draw it. Remember, Lewis structures don't convey three-dimensional information. The first thing when you're trying to assess is your molecule polar or nonpolar is you need to determine whether or not you have polar bonds. Because if you do not have polar bonds, your molecule is automatically nonpolar. There's only London dispersion. If you do have polar bonds, there's one more piece of information you need, but it's the first step. If you don't have polar bonds, automatically nonpolar. Hydrogen, as we learned in the previous example, has an electronegativity of 2.1. Oxygen's, I believe, is 3.5. Yeah. Oxygen has an electronegativity of 3.5. And so when you calculate the difference in electronegativity here, 3.5 minus 2.1 comes out to be 1.4. All right. This is lands squarely in the polar covalent range. All right. Polar covalent bonds are any electronegativity difference between 0.5 and 2.0. All right. So 1.4. Definitely a polar bond. Excuse me. Now, I mentioned that it's not enough to have polar bonds, that the geometry of the molecule has a say in whether or not you have a dipole moment. And here's why. So first, we need to draw the Vesper geometry, the molecular geometry for the molecule. And oxygen has 4 electron groups around it, right? There are 2 atoms, 1, 2, plus 2 lone pairs, 3, 4. So 4 electron groups means that we are dealing with a tetrahedron. And every tetrahedron is the same. There are 2 electron groups that are in the plane of the board or page. Whoops. And then there is 1 wedged and 1 dashed. You may be wondering why I'm drawing this thing all weird up on its side. You will see soon. So we need to arrange our 4 electron groups around our central atom. I'm going to put my hydrogens here and here. And then stick my lone pairs up here. All right. Now, we're concerned here with the molecular geometry. So I'm going to just represent my lone pairs as dots around my central atom. Now, we need to assess whether or not this molecule is polar or nonpolar. Now, we can draw in, there is a partial negative on the more electronegative element, right? Because these bonds are polar. Partial positives down here. And this creates 2 We can draw two small dipoles along the bonds, all right? With the arrow pointing towards the oxygen and the plus sign towards the hydrogen, because it's partially negative on oxygen, partially positive on hydrogen. Now the question, though, whether or not you have dipole-dipole forces in your molecule is not determined by whether or not your bonds are polar. It's, is there a molecular dipole? Now, here's a thing that you need to keep in mind, and that is this. Dipoles are vectors. All right? They're vector quantities, which those of you who have taken physics have dealt plenty with vectors, right? And vectors are quantities that have a magnitude and a direction. So, for example, a quantity that just has a magnitude is speed, 55 miles an hour. There's no direction to that. It's just how fast it's going. That's the magnitude. If you say I'm going 55 miles an hour east, that's a vector because it's not just it's a magnitude that's pointed in a direction. It's pointed east or north or what have you. All right? These dipoles are vectors, and vectors can be broken down into an x component and a y component. So for this vector here, it is the sum of this vector in the x component plus this vector in the y component. All right? If you go over the green distance and then up the yellow distance, it's the same as if you traveled along that dipole vector as drawn. We can break down the other vector along that bond into an x component going this way and a y component going up. All right? Now, when you look at this vector breakdown, the yellow vectors are pointing in the same direction, so they add together. Whereas the blue and the green are pointing in opposite directions, so they subtract from each other. So if you were asked to draw the dipole moment for, if you were asked, does a water molecule have a dipole moment, and if so, can you draw the dipole moment in the molecule? The dipole, overall dipole for the molecule would look like this. The green and the blue parts, because they're going in opposite directions, cancel each other out, right? They subtract, i.e. cancel. Whereas the yellow parts going in the y direction, these add. So the dipole moment for the molecule will look like this. This right here is the molecular dipole. For H2O. So water, the molecule, is polar. It is polar, and that is the dipole. This is the negative end up by the arrow. Right up here is negative. And down here by the hydrogens, this is the positive end of the molecule. All right? So this is, water is an example. With HF, no part of that dipole cancels because there's only one arrow along one bond. Whenever you have multiple bonds involved, they might, like in water, part of them cancel, part of them add, we still have an overall dipole. What you have to watch out for are instances like our next example in which the dipoles of the individual bonds cancel completely, and so you can have polar bonds in a nonpolar molecule. For an example of that happening, check out carbon dioxide. All right, carbon has an electronegativity of 2.5. Oxygen has an electronegativity of 3.5. So the difference in electronegativity here, 3.5 minus 2.5 is 1.0. Anything from 0.5 to 2.0 is polar, so this is definitely, these bonds are polar. That does not mean that the molecule is polar. All right? So, let's look at the Lewis structure here. If you look at your central atom, you have 2 electron groups, which means that this molecule is linear, right? It has a linear geometry. All right. So the Lewis structure that I actually have drawn is the 3-dimensional shape of the molecule. It has its 2 electron groups 180 degrees from each other. Now, oxygen's more electronegative than carbon, right? So one of these dipoles along the bond has the positive end on carbon, the negative end on oxygen, like so. The problem is the other dipole has the positive end on carbon, but the negative end on the other oxygen. And these dipoles are pulling in opposite directions with equal strength, and they cancel. They cancel each other out, which makes this molecule nonpolar, is a non-polar molecule. All right, here's a way to think about it, all right? You've got one oxygen on one end that's pulling on the electrons. It's pulling towards itself. You've got the other oxygen on the other end that's pulling in the opposite direction. They're pulling in opposite directions with equal strength, all right? This is like a tug of war, right, where you have 2 people on opposite ends who are just as strong, equally strong as each other, pulling as hard as they can. That knot in the middle of your tug of war rope isn't going to move one way or another because they're pulling with the same strength in opposite directions, all right? So though their efforts cancel each other out. So even though your bonds are polar, the molecule itself is nonpolar because there is no molecular dipole. All right, there is no molecular dipole in this molecule. So carbon dioxide does not experience dipole-dipole attraction. It only experiences London dispersion. All right. Now, this may leave you wondering. This may raise the question, well, okay, well, how do we know then? If you can have polar bonds but a nonpolar molecule, how do you know? And the answer to that question is this. A molecule with polar bonds will not have a molecular dipole if it has the same group on every position of its electronic geometry. All right? A molecule with polar bonds will not have a molecular dipole if it has the same group on every position of its electronic geometry. What am I talking about? So glad you asked. Here's the answer. So if you have so let's talk about our molecular geometries. If you're linear, here, hang on. Let's start a new slide. Electronic geometry. And actually, I'll put this under here. Versus number of positions. All right. If your electronic geometry is linear, that means that you have two positions. All right? So what are we talking about here? If you have the same group on two positions, that would be like, well, CO2. Linear electronic geometry with the same group, oxygen, on both of the positions. This would be nonpolar. All right? What happens if we replaced one of the oxygens with, let's say, sulfur? These are not the same. Therefore, this molecule would be polar. All right? You have to have the same thing on both positions. Since sulfur is different than oxygen, we will have a molecular dipole. in this molecule. Let's talk about trigonal planar. All right, let's talk about trigonal planar. How many positions do we have? 3. All right. So if you have the same thing on every position, then you're going to be nonpolar. So for example, if you look at the molecule, the polyatomic ion carbonate, we got 2 formal charges up in here. You've got 3 positions with the same atom, the same group on every position. This molecule is nonpolar. All right, that molecule is nonpolar. Let's say you have, let's compare it to another trigonal planar molecule. Let's take a look at formaldehyde. You'll notice that 2 of your positions have the same group, right? 2 hydrogens. But the thing is, that 3rd position has something different. And because one of them is different and has that carbon-oxygen bond is polar, this molecule will be polar. All right? Oops. Shoot. Okay, hang on. I messed up. Sorry about that. Okay. Let's do another example. Let's look at tetrahedral. Right, we've got 4 positions. Jason, great question. And the answer is it does not. So Jason asked, does it matter that there are charges or single versus double bonds? And the answer is it doesn't. All right. The charges will have an influence on other intermolecular forces. For example, there are ion dipole forces that are a thing, but the presence of charges, the presence of double versus single bonds do not affect whether or not that molecule itself is polar. The only thing is, do all the dipoles cancel? And if you have the same atom on every position, the dipoles will cancel every time. So it's non-polar. It's non-polar. Totally. All right. Now, let's take a look at a tetrahedral molecule. All right. If you have, so for example, I'm going to throw a couple tetrahedrons out here. Kate, great question. What if there are lone pairs on the central atom? Let me throw up another trigonal planar example. Lone pairs on the central atom totally have an effect. All right, so let's look at another trigonal planar example. If you look at nitrite, which looks like this. Trigonal planar because it's 2 atoms, 1 lone pairs around the central. We said that in order for the dipoles to cancel, you have to have the same group on every position. Now, a trigonal planar central atom has 3 positions on it, but you'll notice that only 2 of those positions are occupied by oxygens in this molecule. The 3rd position is occupied by a lone pair. For your dipoles to cancel, you need oxygens on all 3 positions, and here we only have oxygens on 2. So because we do not have oxygens in all 3 positions, this molecule will be polar. Totally. Okay, let's take a look now at a couple tetrahedrons. Nope. Now, carbon and fluorine definitely make polar bonds. Carbon's 2.5, chlorine's 4.0. Yeah, Kate, anytime. So these bonds have electronegativity differences of 1.5, right? So they're definitely polar, but because in CF4 we have every position occupied by the same group, they cancel. This is nonpolar. If you replace even one of these with something else that's not fluorine, so for example, I'm going to do CH3F. So we'll throw 1 fluorine on there. In this molecule, well, let me throw in my lone pairs. We have 3 groups, but because the 4th group is not the same in this tetrahedron will be polar. All right? So that's the thing. The only time, if you have, so when you're determining, do you have a molecular dipole? Step number 1 is, are your bonds polar? If you have no polar bonds, you have no dipole every time. If you have polar bonds, before you can declare your molecule polar, you have to check what is your VSEPR geometry. How many positions do you have around your central atom? If you have the same atom in every position, the individual dipoles for the bonds will always cancel. If not, if you don't have the same atom in every position, then your molecule will be polar. And just for completeness, if you're dealing with a trigonal bipyramid, there are 5 groups, and if you're dealing with an octahedron or an octahedral geometry, there are 6. Cool. All right, so that is dipole. We will pick up on Monday with more examples, and also we'll cover hydrogen bonding, and then kind of do the examples where we have all 3 intermolecular forces involved, where we will assign intermolecular forces for each and rank them from lowest boiling point to highest boiling point, etc. Thank you everybody for dropping by. I might see some of you in office hours if you care to come and hang. If not, I will catch you all on Monday. Later.